Are you able to see my PPT?
Yes, sir.
Okay, and my audio is clear, no?
Yes, sir.
Okay. So this is what we were discussing. Initially, we got important outcome from whatever, say, 10, 11 class discussion previously related to heat transfer, mass transfer, and momentum transfer. That important outcome was the most important parameter which need to be discussed or which need to be understood in heat transfer is thermal conductivity and heat transfer coefficient and temperature profile. This is in heat transfer most important parameter. Similarly, for momentum transfer, it is viscosity, friction factor, and velocity profile. These are the most important parameter which need to be understood, which need to be looked for various design calculation in momentum transfer. Similarly, in mass transfer, the diffusivity and mass transfer coefficient and concentration variation, concentration profile are the most important parameter. So in that, in continuation with that, so we have started how to estimate friction factor, heat transfer coefficient, and mass transfer coefficient. So general equations available for friction factor are the engineering correlation. So engineering correlations are of general nature. Friction factor is a function of Reynolds number for friction factor for estimating friction factor. Similarly, for estimating heat transfer coefficient, Nusselt number is a function of Reynolds number and Prandtl number. In Nusselt number, you will have heat transfer coefficient. Similarly, in mass transfer coefficient, Sherwood number is a function of Reynolds number and Schmidt number. These are the general nature of engineering correlation available for estimating friction factor. So here heat transfer coefficient, here mass transfer coefficient. So these are all engineering correlations. So there is no purely theoretical background for deriving this equation. All are experimental observation put into this polynomial equation, and as some dimensionless numbers are involved in this, hence it is called as the engineering. That polynomial engineering is done over a polynomial, slight engineering is done over a polynomial, and that polynomial correlation is called as the now engineering correlation. So most of the equation will not have any theoretical solution. All experimental observations is put into this equation and got this equation, and these are, hence this is called as engineering correlation because of this involvement of some engineering in this, and these are limited. Okay, this limitation will come from whatever the experimental limitation, and then error of the order of 25%. This we have already discussed in last class. Then there can be a two types of reference temperature. One will be a bulk temperature and field temperature. This is also we have discussed for different cases how to define this bulk temperature, bulk velocity, bulk concentration, and for different cases, and then film temperature. This is what we have discussed. Now we will discuss flow over flat plate. What are the engineering correlation available for flow over flat plate? So first of all, consider a case. Okay, consider a case. So this is the length of the plate. This is length of the plate, and there is a stream of fluid flowing over this plate. Okay, stream of fluid flowing over this plate, and bulk velocity of the fluid is v infinity. Then how this Reynolds number is defined for this flow over flat plate? So anybody can give input. What is the Reynolds number for this flow over flat plate? Because for different cases, this flow over flat plate Reynolds number is defined for different situations. Aditya, roll number 5.
Yes, sir.
Yeah, how Reynolds number is defined for such a case? Flow over flat plate.
So generally Reynolds number will be dV rho by mu. So
Yeah, that is flow through pipe.
yes, sir.
Yeah, for flow over flat plate.
So based on laminar and turbulent.
Yeah, what
Yes,
will
sir.
instead of D characteristic length, which length will be used over flow over flat plate?
Length will be used, sir.
Length will be used. So
Yes, sir.
certainly, so here Reynolds number will be X will be used actually. X
Yes, sir.
varies from 0 to L. So this is what I told so many times in a class also. F is a function of Reynolds number. This will be the kind of correlation will be there for flow or flat plate. So, and this Reynolds number is defined as x v infinity rho divided by me. So these are the property estimated at bulk temperature. Bulk temperature and velocity is also estimated at bulk velocity. I'm not calculating what is the, because here velocity is zero and slowly velocity will increase. That variation of velocity is not considered while estimating this Reynolds number. Bulk velocity is considered, that you need to remember. Now you can say that okay, I will take a local value of velocity. Okay, instead of x, I will take a width of the width of the plate for calculating Reynolds number. You can take, you are free to take, but generally then whatever with the literature observation, that you cannot compare with your observation. So if you want to use the data from literature, so you need to follow the nomenclature. So here nomenclature, this x is used. So x varies from 0 to I. So here you can see. So for flow through pipes, I can say that Reynolds number of a flow. Okay, Reynolds number of a flow is 1500. Reynolds number of a flow is 5000. I can say, but here you can see x. Here x equals to 0. So certainly here, according to this definition, Reynolds number will be 0 here. Okay, so and then here slowly Reynolds number will increase. Slowly Reynolds number will increase slowly, and here you will have maximum value of Reynolds number, keeping all other property constant. This is bulk velocity, this is bulk density, this is bulk viscosity. So everything is keeping constant. Reynolds number is increasing. So certainly the you can say information, what information I have. Reynolds number less than 2100 is laminar, Reynolds number greater than 2100 is transient, and Reynolds number greater than 3000 is turbulent. That information will not fix here. That is for flow through pipe only. That is what you need to understand. Okay, you need to understand a system also along with a model equation, whatever. So all the time Reynolds number less than 2100 is a laminar. That is not true here. Okay, here that limitation is some different. That I will tell you what are the limitations of Reynolds number below which you can call it as a laminar flow. What are the limitation of Reynolds number above which you can call it as a turbulent flow. Okay, that we will see. But this is the definition of Reynolds number. Now certainly friction factor is a function of Reynolds number is kind of okay. What this scientist has done, they have estimated a Reynolds number and they have estimated a wall flux, momentum flux, and from wall momentum flux they got the friction factor and they try to correlate this friction factor with Reynolds number, and they observe this friction factor and variation of friction factor with Reynolds number and try to put in a equation. Okay, so for laminar flow and turbulent flow they have different equations. So this for laminar flow, this is the equation they have observed. Local value, in fact they could get a local value of Reynolds number for laminar flow. So with some measurement, so 0.664 Reynolds number raised to half, local value of Reynolds number. This is the only equation which, as per as my knowledge goes, this is the only equation which will have analytical solution also. And so certainly it is experimentally observed equation also, fitted equation also, and it has an analytical. This is the only engineering correlation I am aware of. So which will, because this, even though for laminar flow, okay, laminar flow is easy to just study here for laminar flow first of all, and flow over flat plate. So surface area also is very simple, flat plate and over which flow is there. So it is very easy to model this equation. Okay, very easy to model this equation, and this equation will have analytical solution also. And who has given this equation? This equation is analytically solved by Blasius. Okay, Blasius, Blasius. Okay, this is one of the mathematician who has solved and gave this equation in 1908. Okay, what he has done, he has adopted a couple of method in mathematics. First of all, he has done a similarity solution, and then he has done some other method also, method of combination of variable. So using that, he has derived this equation from first principle, from the definition of wall flux, from the definition of Reynolds number, he has derived this equation, and this is the, as per as my knowledge goes. I'm not very sure that okay, other, because there is for laminar flow through pipes also there are analytical solution available, but it is not clearly analytical. It is the partial analytical, partial experimental. But this can be derived clearly analytically also, analytically using Blasius method. You can say Blasius method, and that too he has given this method in 1908. So he has solved it by two methods. First of all, similarity solution he has adopted, and then method of combination of variable he has adopted, and purely without experimentation he has given this equation. Okay, then this is for turbulent flow only, this is for laminar flow only, and this is for turbulent flow, and this is purely experimentally you can say experimentally model fitting, okay, polynomial fitting equation in the form of f is a function of Reynolds number. So observation, wall flux, observed Reynolds number, try to fit this value to get the friction factor, and friction factor will be equal, and this is purely experimentally derived equation. No theory can predict a thermal complex. As soon as I am going for turbulent flow, so this will be a complex nature of flow characteristic at the interface, and for complex nature of flow characteristic at the interface, it is very difficult to predict the molecular interaction in a fluid, molecular interaction in a fluid, molecular interaction in a fluid and a solid plate. It is very difficult. So this is, there is no theoretical solution available for this equation. Only this has a theoretical equation. This is a experimental equation. Experimental equation means experiments are done, large number of experiments are done, and they have fitted this Reynolds number with a wall flux, and wall flux is related with a friction factor. So friction factor 0.592, Reynolds number raised to 1 by 5. This is what their observation is there. Their observation for turbulent flow. Now, so as I am telling Reynolds number, so you can see according to this definition of Reynolds number, according to this definition of Reynolds number, if Reynolds number less than 500,000, okay, 500,000, it is called as a laminar flow. Okay, if Reynolds number is less than 500,000, as per this definition, flow over flat plate. Okay, so only knowing that Reynolds number less than 500,000, my flow is laminar is not enough. You need to know what is the system. System is flow over flat plate, and Reynolds number is defined. This is the characteristic length. X is a characteristic length where flow direction is x. So x varies from 0 to L, and all other properties are estimated at bulk situation. So bulk velocity, bulk density, bulk viscosity. Here all other properties are estimated for a bulk of the fluid. So with this definition of Reynolds number, if Reynolds number is less than 500,000, it is called as a laminar flow. So this now as far as chemical engineer is concerned, you should just how that in having that information that Reynolds number less than 2100 is laminar flow is good, but you must know the system also. It is for flow through pipe, and all the properties are estimated at average velocity, average temperature, average all viscosity, density, and uh, velocity are estimated average there. Reynolds number for flow through pipe. Similarly, here also, if Reynolds number is less than 500,000, so you should not get confused. There, Reynolds number 3,000 is turbulent, and here Reynolds number 5,000 is laminar. How it is possible? Because all the situation is involved. According to this situation, they are observed that if Reynolds number is less than 500, so most importantly, it is laminar flow. Definition of laminar flow is not changing. There is a flow of say layer to layer. There is no intermixing between layer. Okay, that is what laminar flow is there. So one flow is flowing parallel to another flow, and there is no intermixing. Molecular intermixing is least. Okay, there is no intermixing between layer. That is laminar flow. That definition will remain same. But here Reynolds number is 500,000, there Reynolds number is 21,000. Similarly, if Reynolds number is greater than 10 raised to 8, it is called as a turbulent flow. Okay, Reynolds number is greater than 10 raised to 8, then it is So you can see here REL, here REX, that you need to understand. This is at local value. So certainly flow over flat plate, initially you will get laminar flow and slowly it will change to a turbulent flow, and then you will have transient flow, and then you will have turbulent flow. Okay. So if REL, okay, maximum below this, you will have Reynolds number 500,000. So this is laminar flow. And then if REL, maximum value of Reynolds number is between 500,000 to 10 raised to 8. So whole of the, this is called as a transient flow. Then both will have effect, laminar as well as turbulent. You need to consider how much is laminar flow, how much is turbulent flow. So this is also new thing over flow or flat plate. Both flow can coexist over flow or flat plate. Well, this is not the case in flow through pipe. It will be either laminar or turbulent or transient. But you cannot have laminar and turbulent flow together in flow through pipe. But flow or flat plate, it may happen that so initial part of the plate is experiencing laminar flow, and latter part of the plate is experiencing transient flow, and then thereafter you have turbulent flow. But if say maximum value of Reynolds number is greater than 10 raised to 8, so you can neglect this effect. You can neglect this effect of Reynolds number laminar and transient. So you can consider whole as a turbulent. So that is how the this their observation is there. So once I have this equation, okay, this is the local value of friction factor flow or flat plate. This is the local value of friction factor flow or flat plate for turbulent flow. I can get a Nusselt number and Sherwood number. It is very easy. You can use the, you can say Chilton-Colburn analogy. Okay, Chilton-Colburn analogy you can use, and you can get the equation for Nusselt number, because F by 2 equals to Stanton number into Prandtl number raised to 2 by 3. So F is given, so you can get a Nusselt number. You can get Nusselt number, and instead of Stanton number, you can use a Reynolds number and Nusselt number. That using that correlation, you can get a local value of Nusselt number, local value of Sherwood number. So use, so this is, so as I am telling that this is the only equation which will have a theoretical solution, and theoretical solution is given by Blasius. Okay, Blasius in 1908, and he has used similarity solution and method of combination of variable. So these are the techniques he has used in mathematics. So we are not going to go in details of solution of this. This is equation is very important for us being a chemical engineer. How to get friction factor? How to get friction factor? This is how I can get a local value of friction factor for laminar flow. This is how I will get a local value of friction factor for turbulent flow. Okay, for transient flow, I need to use this also, I need to use this also, both. So up to 500,000 I will be using laminar flow. After 500,000 I will be using turbulent flow equation. But if say Reynolds number is greater than 10 raised to 8 maximum value, then I will be considering whole of the flow is dominated by Reynolds number turbulent flow only, and then you need not to consider this laminar flow. So, and using this and this Chilton-Colburn analogy. Okay, so what is Chilton-Colburn analogy? First of all, this is F by 2 equals to Stanton number into Prandtl number raised to 2 by 3, and this Stanton number is Reynolds number, Nusselt number divided by Reynolds number into Prandtl number. If I put it here, so it will be Nusselt number divided by Reynolds number and Prandtl number raised to 1 by 3. Okay, raised to 1 by 3, that will be equals to F by 2. You substitute this here, and F by 2 equals to Reynolds number, this thing actually. Now you can substitute it here. Okay, so F by 2, and you can get this equation. You try to get this equation. Okay, so combine this and this. Okay, friction factor equals to 0.664 Reynolds number raised to half, and this information F by 2 equals to this Nusselt number divided by Reynolds number into Prandtl number raised to 2 by 3. So certainly you can get Nusselt number, value of Nusselt number. Rearrange the equation, so you will get a Nusselt number. So you rearrange this information. Okay, friction factor equals to this for laminar flow, and for turbulent flow friction factor equals to this. First you try this friction factor. So here you put 0.664 Reynolds number raised to half REX. This is X represent local value of Reynolds number. So, and this will be equals to local value of Nusselt number. Okay, local value of Nusselt number divided by local value of Reynolds number, and this Prandtl number raised to 2 by 3 divided by Prandtl number will be equals to Prandtl number raised to 1 by 3, and rearrange and get Nusselt number, local value of Nusselt number. Yeah, roll number 29, Vedant. So what is the local value of Nusselt number?
I got 0.332 into
0.
Reynolds number to the 332
Huh?
into Reynolds number to the power of 1 by 2
Okay.
into Prandtl number into raised to the power of 1 by 3.
1 by 3. Very good. Correct. That is for laminar flow. Okay.
Yes, sir.
Roll number 41, Mithilesh. Roll number 41, Mithilesh. Roll number 33. Vikram. So Vikram, hope you are listening. You are not responding in a class. This is, I think, 3 or 4 times I called your roll number. Okay. Make a note and keep in your mind, and don't and this will be counted in evaluation. Roll number 41 also, Mithilesh. Roll number 63, Shreyas.
Yes, sir. Am I audible?
Yeah. So what will be the Reynolds number, local value of Reynolds number for turbulent flow?
For turbulent flow,
Because
like
this is
it will
for
be greater
turbulent flow.
than 10 raised to 8, no?
Yeah.
Oh,
No.
okay. Friction
Yeah.
factor. Okay.
Local value. Yeah, local value of local value for turbulent flow. Transient and turbulent, actually it is. Transient and turbulent, local value from this.
Yeah. So, sir, what I have to do? Like, I have to give NUX.
Yeah, NUX equals to?
Sir, it is 0.0296
Very
REX
good.
raised to 4 by 5 and PR
Plus 4 by 5 or
into
minus
PR
4
raised
by
to 1
5?
by 3.
Huh?
So, plus 4 by 5.
4 by
Plus
5
4 by 5, sir.
into?
PR raised to 1 by 3.
Very good. So these are the equation actually. Okay, this will be the this will give me local value of Nusselt number. This will give me local value of Sherwood Nusselt number for turbulent and transient one. Local value REX. This is not REL. REL is a constant, but REX is varying. So here Reynolds number is different. Here Reynolds number is different. Here Nusselt number is different. Here Nusselt number. Local value of Nusselt number. Okay. So how about Sherwood number? Roll number 91, Shubham.
Sir, sir, exactly don't know, sir.
Yeah?
Don't know, sir.
You don't know.
Yes, sir.
So I request you to drop the transport phenomena course.
Sir, I will try, sir. From next class, I will be more attentive.
So certainly you are going to get a FF grade then. If you don't know this, and if you are if you are saying with a proud actually, I can feel proud in your voice that you don't know the answer.
Hello, sir.
Uh-huh.
I will try from next class better, sir. I not join the Saturday
There
class,
is no
sir.
next time. There is no next time in your life. Okay, and this is, you are saying this proudly. That is what I can say proudly.
No, sir. I am not saying it's proudly, sir.
Yeah, it's
I
fine.
will try my best, sir.
It's fine. But I can see the proud. I can hear the proud from your voice, and
No,
equally
sir. I am
proudly
not
I can
saying
say
it
that.
proudly, sir.
Equally proudly I can say that you cannot get more than FF grade in transport phenomena. So why you are wasting time in transport phenomena? This is what I am also saying proudly. I know you cannot get more than FF grade.
I will try best from next class,
What
sir.
is try best? This is the slide. I am giving this information. I am giving this information. If you are not giving me this equation, so what is point in trying? What you are
I
going to try then? What you are going to try?
I will
This is
wait in
not
my
a
wait in,
LKG. Na? This is
sir.
not
I will
LKG
try.
and 1 plus 1 will be 2.
I can Stanton Sherwood number
It's
equal
fine,
to
fine. Okay. You don't know.
Stanton
You
number
keep
into
your
Renault number
crowd
into
with you.
seat number.
Yeah, roll number
Hello, sir.
41. Yeah, 49. Harshvardhan.
Yes, sir.
So what is the Sherwood number, local value of Sherwood number?
Sir, I'm getting as 0.332
Uh,
into Reynolds number raised to 1 by 2
uh,
into Scranton number raised to 1 by 3.
Prandtl number. What number you told?
Yes, sir. Scranton number raised to 1 by 3.
Scranton number.
Sorry, sir. Schmidt number, sir. Sorry,
Yeah,
sir.
that is not a Scranton number. This is Schmidt number. Okay, that is correct. Actually. Very good. Roll number 63, Shreyas.
Hello, sir. Yes, sir.
Huh. Yeah, Shreyas. Yeah, tell me what is for turbulent flow here? Equation app.
Uh, Sir, it will be same as of Nusselt number, just instead of Prandtl number, it will be Schmidt number.
Yeah, very good. So it is same. It is same 0.33 through Reynolds number raised to half, Schmidt number raised to, and this 100 times I told that Prandtl number is similar to the Schmidt number in heat transfer and mass transfer. So just you need to replace this. That also logic you don't know. If this two slide you cannot combine the information. So what is point in doing wasting your time in taking transport phenomena? I'm sure I am proud that okay I am proud that I can judge. I can judge from today itself that these people who are not able to derive this equation, they are likely to get FF grade. That I know. Okay. So this is the local value of Nusselt number. So I can get local value of Nusselt number, local value of Sherwood number for laminar flow from turbulent flow. And this is the Reynolds number should be less than 500,000, and this will be Reynolds number for greater than say 500,000. So from 500,000 to 10 raised to 8, it is called as the transient, and greater than 10 raised to 8, it is called as a turbulent. And some more limitation will come into picture. What are these limitations then? Any additional limitation I need to add? Roll number 68, Mitu.
Yes, sir.
Yeah, any additional limitation I need to add along with this?
Sir, any additional, sir, like a Prandtl number,
limitation of
Prandtl,
using this equation.
yes,
Yeah?
sir, like a Prandtl number greater than 0.6 and less than
Very
60,
good. Excellent.
and
So,
Schmidt number,
yeah. Very good.
Schmidt
Thank you very much. So
yes,
all the limitation of Chiltern-Colburn analogy will apply here, because I am using Chiltern-Colburn analogy here. So all the limitation along with this basic limitation, okay. Prandtl number between 0.6 to 60 and Schmidt number between 0.6 to 3000, along with other geometric limitation of Chiltern-Colburn analogy also apply here, because I am using Chiltern-Colburn analogy. So these are the limitation by, you can say, Blasi as first time he has observed, he has given this limitation, and this is limitation coming from Chiltern-Colburn analogy. I have combined the information, so limitations will be also combination. Combination of both will be the limitations of using this equation. You can use this equation with this limitation, you can use this equation with this limitation and all. And most of the time I'm not interested in local value of friction factor, local value of Nusselt number, local value of Sherwood number. So how to get a average value? It will be average over this length. Okay, because this is the function of length, this is also function of length. So rex, here you can see x, this is the function of length, this is also function of length, and this is also function of length. Everything is a function of length. So here say friction factor local, it is giving me local value of friction factor. Here friction factor is different, here friction factor is different, here friction factor is different. But for design calculation I am not interested in friction factor most of the time. I will be interested in average value of friction factor. So how to get the average value of friction factor? I can sum it over length, and divided by length. Okay, sum it over length and divided by length. That will give me a average value of friction factor. So how to get the average value of friction factor then? Can anybody give me idea? Here, roll number 88. Pritesh.
Yes, sir.
Yeah, can you give me idea how to get the average value of friction factor, average value of Nusselt number?
So, sir, we can see since we require it along the entire length, so we can use integration.
Yeah, very good.
Taking
Integrate.
dx.
Integration with summation. Okay. What do you mean by integration? Integration with summation. Okay. It is
Summation of
continuous.
infinitely small element.
What? Yeah.
Sir,
So you
integration
will
is
take a
summation.
differential length. You will integrate.
Yes.
That is just a summation divided by length.
Yes, sir.
That will give you average value. So I can get the average value. Say if Reynolds number is less than 500,000, complete plate will have, you can say, this is for local value of friction factor I can use. So I can get a delta x differential thickness and integrate this friction factor from 0 to L divided by L. So this will give me average value of friction factor. Say Reynolds number, and this is what, so this L, so substituting L equals to REL and X equals to REX. Okay, so X will be equals to REX in terms of Reynolds number. Just for this is just a mathematical manipulation. Okay, when L equals to REL, so X will be equals to REX. Substituting this, so it will be easy to integrate. If Reynolds number is greater than 10 raised to 8, so certainly laminar flow will be there over a plate, but I can neglect this. Okay, you can see order of magnitude 500,000 and 10 raised to 8. This Reynolds number, final value of Reynolds number is greater than almost fourfold of magnitude. Okay, order of magnitude is 4 times greater than this 500,000. So I can neglect this. Then I can just consider a turbulent flow. I can get just consider a turbulent flow because final value of Reynolds number is far much greater than 500,000. So contribution of friction factor because of this is negligible. So I can consider only turbulent region throughout a plate, even though there will be a laminar flow initial, but that contribution is very negligible. So you can see, okay, this will be a, again here I can put just a turbulent, okay, turbulent, and integrate it over. Substitute L equals to this thing, and if my Reynolds number is between 500,000 and 10 raised to 8, I can consider both. Okay, both laminar as well as turbulent. Okay, laminar as well as turbulent. For Reynolds number between 500,000 and 10 raised to 8, I can consider laminar and turbulent. There will be a critical length. So critical length means length till which Reynolds number is reaching 500,000. So till that I will be considering laminar, local value of laminar. After critical length, this will be a turbulent. I will consider turbulent. Both equation we will consider if Reynolds number is between this and this. Again, substituting x equals to Rex. So I can rearrange this equation and get the value of average value of friction factor. So this will be the average value of friction factor for laminar flow. This will be the average value of friction factor for transient. Means it is going from laminar to turbulent slowly, and this will be a average value of friction factor for a you can say turbulent flow. Okay, now substitute this FEX. Okay, you already have FEX, so substitute this value. You already have turbulent. Okay, FEX for turbulent. So this is what I am saying. Okay, this is FEX for laminar 0.664 REX raised to half, and this is for turbulent FEX 0.0592. This thing for, and substitute this and get the average value of Reynolds number for laminar flow, for turbulent flow, and for transient flow. Okay, substitute this. Roll number 64, Shubham.
Hello, sir. Yeah.
Yeah. What is average value of friction factor for laminar flow?
Sir, it will be 1.328 into RE to the power minus 1 by 2.
REL now. It will not
RE,
be REX. It will
yeah,
be
over the length.
REL. Okay.
Yes, sir. Yeah.
That will give you average. And how about turbulent flow?
It will be 0.074 REL to the power minus 1 by 5.
Are you just reading or you have estimated this, Shubham?
Yeah, sir, I have integrated.
Okay, very good, very good. Okay, so don't use the shortcuts. How about this?
Sir,
So critical REC will be 500,000. This value of
Yeah.
REC is 500,000.
okay.
REC equals to 500,000. Below which flow is considered to be Reynolds laminar. Above which flow is considered to be a non-laminar flow or turbulent flow. REC equals to 500,000. Yeah, roll number 47, Gurupreet.
Yes, sir.
Yeah, what is value of average value of Reynolds number for this?
Sir, like, sir, I'm getting 0.007 REL to the power minus 1 by 5 and 1740 REL to the power minus 1.
Okay, so I don't remember maybe. Okay, but this is what you can say for laminar. This is the value for laminar and this is the value for turbulent. So now this is for laminar 0.128 REL raised to minus half REL. You can see here REL, Reynolds number at the end of the plate. So this is 0.074 REL raised to 1 by 5 minus 1743 REL raised to. This is what you got, Gurupreet?
Yes, sir. The first term is 0.073 I'm getting,
Okay.
and the next term is 1740.
Yeah, very good. Excellent. And this is 0.004 REL raised to minus half. This is the average value of friction factor, not local value of friction. Average over a plate. This will be a local value of friction factor in laminar region. This is the local value of friction factor in a turbulent, and this is the average, and this is true if my Reynolds number is less than 500,000. I can use this. I can use if my Reynolds number is greater than 10 raised to 8. If my Reynolds number is between 10 raised to 5 and 10 raised to 8, I can use this. Okay. Now using Chilton-Colburn analogy, I can get the average value of Nusselt number, average value of Sherwood number, average value. Use Chilton-Colburn analogy for average properties. Average property. So you can get a Nusselt number for you can get a Nusselt number, average Nusselt number, that in turn average value of heat transfer coefficient, average value of Sherwood number will give me average value of mass transfer coefficient. Here, roll number 22, SBSVS. Roll number 22.
Hello?
Yeah.
Hello, sir.
So, what is the average value of Nusselt number for laminar flow?
Sir, I'm getting for laminar flow 0.
Zero.
No, answer.
You use this and use a Chilton-Colburn analogy.
Yes. 0.6 into REL
Power
1 by 2
uh,
into Prandtl number by 1 by 3.
Very good. And how about this?
So it is I'm getting 0.037
37. Okay.
REL power 4 by 5 minus
Okay.
871 Prandtl 1 by 3.
And this whole multiplied by Prandtl number raised to 1 by 3. Whole.
Yes, sir.
Only not to this.
Yes, sir.
Okay. This is whole multiplied by Prandtl number. That you should remember. Otherwise, you will make a mistake. And how about this turbulent flow?
0.037 REL power 4 by 5 and Prandtl number power 1 by 3.
Okay. So now you can use Chilton-Colburn analogy, exactly same thing. So this is what you will get actually. This is what you got.
Yes, sir.
Okay.
Yes, sir.
This is what you got.
Yes, sir.
This is what you got.
Yes.
And this try to get this Sherwood number. So this is what if Reynolds number. This you can say REL. This you should remember. I'm telling you so many times. These are all local values of friction factor. Okay, these all are local values of friction factor. But most for design purpose, most of the time we will be using this average value of friction factor, average value of Nusselt number. So you will never see in heat transfer that heat transfer coefficient value. Even though it is mentioned heat transfer, it will be average value of heat transfer coefficient, average value of mass transfer coefficient. Many times it will be mentioned also average value of heat transfer coefficient, average value of mass transfer coefficient. But this is what. So what is the limitation? This is true. This is true for flow over flat plate, and this is one of the equation which will give me average value of friction factor, average value of heat transfer coefficient, average value of Sherwood number for laminar flow, for transient flow, and for turbulent flow with all the limitation of Chilton-Colburn analogy. So I can use this equation for estimation of design friction factor, heat transfer coefficient, and mass transfer coefficient for flow over flat plate. And these are not the only available equations for flow over flat plate. In fact, you can do the experiment. You can propose some different constant instead of 0.138. You can you may get something else. Okay, so you may get something else. Say REL raised to instead of half, you can 3 by 2, and some different constant. This say A and B can be different for your thing, but every time the nature of the equation will be similar in engineering correlation. Friction factor is a function of Reynolds number. So here you can say friction factor is a function of Reynolds number. Friction factor is a function of Reynolds number. In heat transfer, Nusselt number is a function of Reynolds number and Prandtl number. Here also you can see Nusselt number is a function of Reynolds number and Prandtl number. Nusselt number is a function of Reynolds number and Prandtl number. Sherwood number is a function of Reynolds number and Schmidt number. Sherwood number is a function of Reynolds number and Schmidt number, and Sherwood number is a function of Reynolds number and Schmidt number. So these all are limitation. These are the limitation coming from the observation of flow over flat plate, and these are the limitation coming from Chilton-Colburn analogy. So with this limitation, I can use this equation. So just knowing this equation is not enough. Okay, knowing this equation is as important as knowing the limitations where I can use this equation. That is also as important as knowing this equation. So only knowing this equation, that friction factor. Now you assume that you have a tool now. The friction factor is 0.1328 Reynolds number raised to half. Now you can use this in flow through pipe. You can use flow over sphere. You can use flow over tube, and everywhere you can use. That is not the case. With the limitation, that too limitation from current experimentation as well as limitation from Chilton-Colburn analogy, Chilton-Colburn observation. So these are the engineering correlation I can use. So I am repeating same thing again and again. Just knowing this information is not enough. So I can estimate Nusselt number. So which situation it is applied? Which range of Reynolds number, Prandtl number, Schmidt number it is applied. That is also very, very important. Very, very important. So if you are you want to calculate some system for some system the heat transfer coefficient, first you need to search for a engineering correlation which will fit to your requirement. Say flow through pipe with corrugation, higher Reynolds number, Prandtl number, range of Prandtl number, range of Schmidt number. So certainly you need to go in literature and get the appropriate engineering correlation which will fit to your requirement, and then use that correlation. I will say that there can be thousands of engineering correlation available, thousands of engineering correlation, and certainly you can get the engineering correlation of your requirement. Okay, if you are not getting, then there is no other way. There is no other way. Doing experiment yourself, in lab level. This is why they are related with a dimensionless number. Okay, you can do the experiment in lab level, and same engineering correlation can be used in larger level also, industrial level. Okay, so so that is the importance of dimensionless number. So whatever observation you are making in lab level can be directly used on industrial level also. Scale up. Okay, for scaling up, you need not to do experimentation on industrial level. You can do an experiment in lab level and derive appropriate engineering correlation, and that engineering correlation can be used on industrial level for a designing purpose, and accordingly you can design whatever industrial parameter needed for your heat transfer, mass transfer, and momentum transfer. So this is flow over flat plate. So we'll solve couple of problem, and then we'll see what are other engineering correlations available for flow over flat plate also, and for other systems also. So anybody has any confusion, anything to add over this engineering correlation? Any important point which can be added over this engineering correlation, or you might be having any confusion, anything? Everybody understood? No question at all?
Sir, I had a question.
Your roll number?
59.
59. Tell me.
Sir, what if we have a condition where even after we have checked the limitations, there are two sets of equations that are applicable to any system that we want to design. So then
Okay.
in such a case, what should we do to select the best set of equations?
Yeah, you can use both. Okay, you can use both. Get the value of design parameter and use the limiting value of design parameter.
Okay,
So
sir. So
say,
the one that is
you say,
best.
just I will give you example. One set of equation is giving me surface area equals to surface area for heat transfer required is say 4 meters square. Okay, surface area for heat transfer required is 4 meters square, and another set of equation is giving, certainly there can be plus minus 20 as high as possible, plus minus 25%. Say one set of equation heat transfer coefficient is giving me surface area required for heat transfer is 4 meters square, and another set of equation is giving me surface area required for heat transfer is 4.2 meters square. So I should use a limiting value. Which is limiting value? 4.2 meters square is a limiting value. Okay, so lower value is not a limiting value all the time. It is based on situation. Okay, because if one equation is telling 4 meters square, another equation is 4.2 meters square, certainly 4.2 meters square involve that 4 meters square itself. Okay, so both will be enclosed. Likewise, you can use a limiting value, or you can use an average value with a factor of safety at the end. add factor of safety 20%. So both will be involved actually. Both will be considered that time. Is it okay?
Okay, sir, got it. Thank you.
Okay. Yeah, anybody else? Okay, then thank you very much for attending this class. We'll continue our discussion in next class for this estimation of parameters using engineering correlation.